How did it all begin? How did this universe in which we live come to be? The story begins in the early 20th century with Georges LeMaitre, who originated the concept that an expanding universe could be extrapolated back to a point. Then came the observations of Edwin Hubble that indicated rather clearly that the universe was indeed expanding. Then there were other discoveries, such as the cosmic microwave background radiation, which is literally the afterglow of the Big Bang. But there are mysteries still. There comes a point where we can no longer study the Big Bang directly, a point where everything becomes opaque. This and other questions have led to a number of different models for just how the Big Bang played out. My guest today specializes in the physics of the early universe and unraveling just what happened.
You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Neil Turok. Dr. Turok was a professor of physics at Princeton University and chair of mathematical physics at the University of Cambridge. He was the director of the Perimeter Institute in Ontario. His research focuses on developing fundamental theories of cosmology and new observational tests. With Stephen Hawking, he discovered instanton solutions describing the birth of inflationary universes. With Paul Steinhardt, he developed an alternative cyclic model for cosmology whose predictions are so far in agreement with all observational tests. Turok was awarded the James Clerk Maxwell Medal of the Institute of Physics. In 2003, he founded the African Institute for Mathematical Sciences in Cape Town. For his scientific discoveries and his work developing aims, Turok was awarded a TED Prize in 2008.
Dr. Neil Turok, welcome to the program.
Thank you.
Now, Doctor, you work with the very earliest beginnings of the universe, the Big Bang.
Yes.
And there's a brick wall.
Yeah.
There's a brick wall with the Big Bang where we can only see, I believe it's about 300,000 years or something like that, and that we can see. And then it becomes opaque. How do you get past that? How do you get past that wall in physics of what you can't observe?
Right. So we can see back about 13.7 billion years. But then, as you say, before that, there's about 400,000 years between the Big Bang itself and the era where the universe becomes transparent. So there's this opaque boundary of about 400,000 light years thickness, which surrounds us. And as you say, it's like a brick wall. We find it hard to see through it with light. The problem is the early universe is so dense and full of charged particles that it makes it obscures what happened, at the very beginning. However, there are ways through it. And one of the observational ways to see the beginning of the universe is to use gravitational waves, which have only recently been detected by laboratories here on Earth. And these gravitational waves are not scattered by the dense material of the early universe. So if we're able to measure gravitational waves, they basically give us a way of looking right back to the beginning of the universe itself. And so the science is early. The sensitivity of current detectors of gravitational waves is insufficient for us to really see what happened, but it's a very, very promising direction. And for theorists like myself who make theoretical models of what actually happened at the Big Bang, it's very encouraging to know that in 10, 20, or 30 years, we will be able to test these ideas in experiments and observations.
Now, as a theorist, what do you think actually happened?
I've worked on a number of different possibilities. I have a fairly open mind. What I want to know is the truth. And so the whole point of doing science is to discover that and not to go on the basis of prejudice or preconception. So I am most interested in theories which can be proven wrong, because those are testable theories. And you learn, even if you prove your idea wrong, you learn something in the process. So I think there are a number of possibilities. There's a very popular paradigm called the theory of inflation, which has really dominated the field of cosmology for the last 3 decades. But I find it rather unconvincing myself, based on a lot of additional ingredients which are sort of added by hand to the basic Big Bang picture. And it doesn't really answer definitively what happened at the beginning. It's kind of a theory of what happened just after the beginning. And what is postulated is a process of kind of growth and smoothing of the universe to make it into something like what we see. But for me, the explanation is a little bit too ad hoc, and it's not beautiful enough, quite frankly. I think there is nothing in nature more beautiful than the universe. It's astonishingly simple on large scales. So what I like to say is the universe is the simplest thing we know of in the universe. It sounds paradoxical, but it is indeed amazing that as you go to larger and larger scales in the universe, what you see is increasing simplicity. So that, for me, demands a very simple hypothesis as to how it began. And so that's what I've been exploring. Much simpler ideas than inflation, which seek to explain the very beginning.
Now, how does that work? The universe, at its very biggest scales, is simple and elegant,
Yes.
as you were describing.
Yes.
And then on other scales, though, smaller scales, it gets
Yeah.
increasingly messy. Why is that?
Right, that's the basic puzzle. You might have expected that as we began to probe the universe at larger and larger scales, what we would discover would be more and more complexity, right? So you think of the universe as built out of Lego building blocks, maybe atoms and elementary particles, which are reasonably simple objects. And as you combine them, you get, of course, many complicated structures. You get molecules, you get cells, which are the basis for life, you get living organisms, so complexity certainly does grow as you go to larger scales. The puzzle is that as you go to really large scales, the complexity seems to disappear again. And so the universe on the very largest scale almost looks as simple as an elementary particle. Now, what do I mean by that? I mean that if you look in different directions on the sky, the universe is very, very similar in all these directions to about 1 part in 100,000. The density of the universe is the same in all directions on the sky. And so it's remarkably uniform. And even the non-uniformities, the fact it's not quite the same in each direction, those non-uniformities take a very simple statistical form. They look like random ripples with a very small amplitude and a very simple spectrum, meaning that the ripples of different sizes have almost the same strength, and then they're randomly superposed. So it's like a pattern of waves you would see on the surface of the sea, except when you analyze this pattern in the most possible detail we can, we find that it's the simplest kind of pattern you could get. Superposition of waves of almost the same strength or amplitude on all scales, across all scales. So the large-scale universe is very much simpler even than a complicated molecule like DNA. To describe a molecule like DNA, you would need quite a few numbers, whereas the large-scale universe requires approximately 4 numbers to describe it. One is the strength of these ripples, which I've described. The second is the relative abundance of particles of the type we are made of, called baryons. These are neutrons and protons, the stuff which atomic nuclei is made of. And then the relative abundance of those nuclear particles to particles of light or photons, that's one number. Then you have dark matter, for which we have a new explanation based on this simple Big Bang hypothesis, which I mentioned. And thirdly, there's dark energy, which is a kind of energy that fills all of space in the universe, and it's absolutely uniform in space and in time, just a constant. So these four numbers describing the different forms of energy in the universe, the light, the nuclear matter, the dark energy, and then the fluctuations, the structure in the universe, those four numbers are all you need. So the universe is really incredibly simple on large scales, and I do believe that simple phenomena, require elegant solutions, elegant theory which explains the simplicity. And so these observations, which have really been made only in the last few decades, are incredibly encouraging to sort of crazy people like me who are looking for an answer, who are looking for a theoretical framework which ties this all together in an absolutely compelling way that will convince everyone.
A sort of, once again, elegance. If you come up with an elegant, simple solution that works, then you're there, or at least closely there.
Yeah.
Now, dark matter, you mentioned that in your thinking there's an explanation for it. What is it?
Well, okay, so as I keep mentioning, the last 10 years, the focus of my research is to look for simple explanations. And by simple, I mean elegant, minimal, mathematically rigorous, but with as few assumptions as possible and able to fit the observations. So our picture of the Big Bang, maybe let me step back a little bit. How can you explain the coming into being of the whole universe? That almost sounds impossible, because the laws of physics describe how the universe evolves in time. And when you say the universe came into being, there wasn't any time before it came into being. So, you're almost immediately at a contradiction. The theory we have proposed is based on an analogy, because often nature uses the same principles again and again, and this is especially true in physics. So rather than thinking about the universe, let's think about the coming into being of a particle. Is it possible for an elementary particle like an electron to come into being when there was no particle before? And the answer is yes, it is possible, and it happens all the time in the laboratory. What you see in experiments is the creation of particle-antiparticle pairs. So for example, if I turn on a very strong electric field, if I do have a charged particle, the charged particle will be accelerated by the field and fly off, at increasing speed in some direction, in the direction of the field. Now imagine you had no particle and you turned on a strong electric field. What happens is the field literally drags a particle out of the vacuum, and so the particle goes one way along the field, but it also drags an antiparticle out of the vacuum, and the antiparticle has the opposite electric charge and travels in the opposite direction. So this is a well-established process that electric fields can create particle-antiparticle pairs out of the vacuum, out of nothing. So our theory was really built on the idea, well, maybe that's what happened at the beginning of the universe. Maybe it's possible to, in effect, drag a universe out of nothing. And I'll talk about what does the dragging later. The electric field pulls particles out the vacuum, but in our case, it's really the dark energy which does that. But the implication of this model is that there would be two sides of the universe. One side, if you like, full of matter, ordinary matter, and the other side full of antimatter, just as in the particle-antiparticle pair. So we began to explore this hypothesis. We had to check many things, that it's consistent with what we know about gravity, about particle physics, and we found it works remarkably simply and has certain features which other scenarios like this inflation scenario don't have. And then one of the surprising consequences of this picture is it gave us the simplest yet explanation for the dark matter. So the dark matter, if you look at what we know about physics today, we know about various types of particles and how they couple to forces and through the forces to each other. Now we already know that there's a particular kind of particle called a neutrino, which couples very weakly to other forms of matter. So for example, a neutrino can travel straight through the Earth without colliding with any particle in the Earth because it interacts so weakly with other matter. For this reason, it's called a ghost particle. It really, and these things are produced in laboratories, and with enough effort, you can detect them. And so this is, well-established physics. Based on the properties of the neutrinos we know, we can infer that, which are called left-handed particles. And the reason is if you hold out your left hand and point the thumb in some particular direction, then the other four fingers, turn around the thumb in a certain rotation. And we say left-handed is because when the particle travels in the direction along your thumb, it is spinning in the direction signified by your other four fingers. So there are left-handed neutrinos, which we see all the time in laboratories. But we also infer from these experiments that there are right-handed neutrinos, okay? And the right-handed neutrinos are more ghostly because they literally don't couple to anything, any forces, apart from gravity. The only thing they couple to is gravity, and actually something called the Higgs boson, which is a very, very weak force indeed. So these particles were sort of inferred from all the experiments people do in high energy physics labs. What we realized is that one of the right-handed neutrinos, which we are almost certain does exist, was the perfect candidate for the dark matter in the universe. Now, before us, people hadn't been able to calculate how much of this particular right-handed neutrino would be in the universe because it's so weakly coupled, it isn't easily created by other particles. So it turns out this very odd right-handed neutrino, which we're almost sure exists from multiple experiments, we could, with our picture of the universe sort of being pulled out of nothing, this universe, anti-universe pair, we could actually calculate how many of these strange right-handed neutrinos were present just filling the universe. And when we worked through the numbers, we found a number which allowed the theory to match the dark matter which we see perfectly. So this is really the most economical explanation yet for the dark matter, because once you explain the Big Bang, and if you assume the known physics we already know from laboratories, then this right-handed neutrino turns out to be an excellent candidate to explain the dark matter. We don't even need any more ingredients in the physics we already know.
Now, one of the vexing problems, though, is that dark matter is all we know about it is from its gravitational influence. So these neutrinos, these right-handed neutrinos, are responsible for that excess gravity, right?
That's right. That's right. So it's a very economical explanation, but you're right. We need further predictions to verify the theory, right? And if you can't see the stuff, all you see is its gravity. What's the next step to verify that your explanation is correct? So we have a prediction. In fact, there are several predictions, but one of the most interesting is that if one of the right-handed neutrinos is stable and forms the dark matter, it follows from standard physics, which we didn't invent, we merely interpret. It follows from standard physics that one of the left-handed neutrinos is exactly massless. It cannot have any mass at all. And this is something which current experiments are checking. So the left-handed neutrinos have very tiny masses, and so far it is known that those masses are very small, but it is not known exactly what they are. All that's measured is the differences of masses. The absolute values of the masses are not measured, but they will be over the next decade. So actually, it's amazing the way you measure neutrino masses. The most accurate way now is to use the cosmos, because these neutrinos are present throughout the cosmos, and the way they clump under gravity depends on what their mass is. You see, if they're very light, then they're essentially zipping around at the speed of light. If they're massless, they have to go at the speed of light, and that means they don't clump very efficiently. So our measurements of the cosmos are now so accurate that we can actually see this effect, that the neutrinos are not clumped. They would if they had a mass. So it turns out that over the next 10 years, galaxy surveys and measurements of the radiation from the Big Bang will be able to test if one of the neutrinos is very nearly massless. And if it is, that will confirm the basic prediction of our. Now, but there's another prediction which was in a way even more exciting, which is so we wrote this paper saying, the right-handed neutrino can be the dark matter, and this is its mass. If it is the dark matter, this is its mass. We can predict the mass of the particle exactly. And it was, 400 million times the mass of the proton. So 480 million times the mass of the proton. We wrote the paper, that was the prediction. So it turned out, unknown to us, there were experimentalists in the Antarctic who were looking for signals of decaying particles. And as these particles are very heavy decaying particles, they would emit very high energy particles which would give rise to showers of charged particles in the atmosphere. And they designed a very beautiful and clever balloon-borne telescope to see the signal of those showers. Unknown to us, they had detected two events at exactly 480 million times the mass of the proton, which they could not explain. Okay. And so they immediately, contacted us and said, wait, we've seen two particles decaying like that. Now, there's a contradiction, because I told you already we need these particles to be stable to explain the dark matter, meaning they have to have lasted at least the lifetime of the universe. Obviously, this experiment is seeing the byproducts of the decay of a particle with the same mass. So what happened? So it is conceivable that these particles are, very stable, but not absolutely stable. And so they would decay at some slow rate. And they could have explained the events in the Antarctic. So we're still thinking about that. At the moment, it seems difficult to reconcile our first hypothesis with their experiment, because we predicted they wouldn't decay. They're seeing the decays. They've only seen two of them in about 4 years, so they're not decaying very quickly. But that's a very tantalizing clue. And if it turns out we're able to explain those events, and of course, if they measure more of those events, we would actually have real convincing, completely compelling theory of the dark matter, and we would be seeing the decay products of the dark matter. So all of this is up in the air. It's all frontier science, but very exciting, and it may be verified or it may all go away. And we'll have to see.
Now, this idea of a weakly interacting particle.
Yes.
And the idea of, this goes back to WIMPs and things like that,
Yeah.
that people used to talk about in
Yeah.
regards to this.
Yes.
Now, that interaction.
Yes.
would suggest that it's weakly or almost not interacting with the Higgs field, right? To get back to the Higgs boson.
Yes, very good.
That field is not lending this particle mass.
That's correct.
But yet it's still responsible for the gravity, right? How does that work?
Yeah, very good questions. Okay, so in the standard model, and as I say, our theory is, I would say, is much more compelling than the theory of WIMPs or indeed any other theory of dark matter, because before our work, the only way people had to explain the dark matter was to add something else to the standard model, right? And there are 1,000 different things you can add, and each one could explain the dark matter. So we are trying to explain the dark matter by adding nothing, by just taking the absolute bare minimum of what's necessary for the standard model. And what we found is that there's this little corner of the standard model involving these right-handed neutrinos, which with some modest assumption, but adding nothing, with a modest assumption that right-handed neutrino can be the dark matter. So let's look a little bit at this right-handed neutrino. Now it's in the most general form of the dark matter. The right-handed neutrinos are only allowed to couple to two things, the Higgs boson and to gravity. But what we've done is reduce the model by insisting that one of the three right-handed neutrinos only couples to gravity. It doesn't couple to the Higgs boson at all. And its left-handed partner, if you like, for every right there's a left, the left-handed one is massless, the right-handed one is stable. These two things go together, and neither of them couple to the Higgs boson. So where does it get its mass from, if not from the Higgs boson? And the answer is that because the right-handed neutrino doesn't couple to any other forces other than gravity, you are allowed in the standard model of particle physics to give it a mass, which can be very big, and that is what we call a bare mass. It's just put in to the model. It's not disallowed. You see, the standard model is sort of a very beautiful construction which disallows masses, according to which the only way mass can be obtained is through the Higgs boson. And that's true for electrons, for quarks, and for the left-handed neutrinos. They can only get masses through the Higgs boson. But for the right-handed neutrinos, you can actually just, because they don't couple to any of the forces, you're allowed to just give them a mass. And that mass can be very, very big. And so that's what we do. We give that right-handed neutrino a mass. It does not come from the Higgs field, but one is allowed to do that by the normal rules of the standard model of the sort of consistency of physics. This was the fact you could do that was discovered in the 1970s. It's called the seesaw mechanism. It very naturally explains. So you're allowed to put in these masses of the right-handed neutrinos. They are allowed to be very heavy masses. And then there's what's called the seesaw mechanism. As you make the right-handed neutrinos heavy, the left-handed neutrino masses get very, very small. And what we observe in nature is indeed that the left-handed neutrinos do have very small masses. And so this is a success of the seesaw mechanism. You give the right-handed neutrinos masses, big masses, and as their mass gets bigger, the left-handed neutrino masses get smaller. So that's the seesaw, and it's very well motivated from particle physics we've known since the 70s. So what wasn't noticed is that one of these very heavy right-handed neutrinos is the perfect candidate to be the dark matter.
Now back to this idea of the universe at large scales being very, very simple. How does entropy play into this? Does the universe get simpler as time moves on?
Yes, that's a wonderful question. Indeed, the universe is extremely simple at large scales in space, right? As I've explained, when you look outwards, the further you look, the simpler it is. It's basically almost uniform, with this extremely simple superposition of waves on top of it, scale invariant random waves, very small amplitude. So it's simple at large scales in space. It's also unbelievably simple at large scales in time. Now, what do I mean by that? Well, we live 13.7 billion years after the Big Bang. But if we go to 20 billion years or 30 billion years after the Big Bang, based on what we see now, we can forecast what the universe will look like. And what is happening, what will happen, is that the dark energy, which is absolutely constant in space and constant in time, that dark energy will take over the universe because everything else is being diluted away. The matter, the radiation, the density is falling, the number of galaxies, these are all being diluted by the expansion of the universe. The dark energy is not diluted by the universe's expansion. So in the far future, basically it'll be a universe full of nothing but dark energy, absolutely smooth, no galaxies or objects. And so indeed, the universe in the far future is extremely simple. Now, what about entropy? Well, entropy is supposed to grow. According to the laws of thermodynamics, the entropy never decreases. Disorder always grows. And then it turns out that gravity is able to contribute to the entropy. And so you have two types of entropy. You've got the entropy in ordinary matter, and that's maximized when the ordinary matter is as smoothly distributed as possible. But then you have the entropy in gravity, and the entropy in gravity is maximized when this dark energy takes over everything else. We say the entropy is maximized in de Sitter space, and de Sitter space is this kind of completely smooth, uniform universe dominated by dark energy. So it turns out that the dark energy future of the universe is the maximum entropy state possible. And so the universe started from zero entropy at the Big Bang, an extremely simple beginning. It ended up in this maximum entropy state, which is also extremely simple. And all the complexity is both in space and in time. So we live in the middle. We're literally in the middle of the universe around us, obviously. That's what we can see. So we're in the center of it. But we're in the center of it in another sense. We're in the center of it in scale, right? So the very tiniest things are elementary particles. The mesoscopic things are us, and that's where all the complexity is. And the very largest scale things, both in space and time, is the dark energy, which is, again, extremely simple. So, this picture is kind of the return of the notion that we are special. We live in the center of the universe. This was discounted by the discoveries in the Middle Ages, that people used to think that the Earth was the center of the universe, and then we discovered that no, the sun is the center of the solar system. And then we discovered lots of other suns and stars and galaxies, and that made us feel more and more ordinary. But in fact, we're not that ordinary because we live in the middle. And the universe is, and the middle is where all the complexity is. So I would say, we physicists are just getting our head around this notion. It's not fully understood yet quite what the simplicity means at very large scales. But I believe it's absolutely as fundamental as the simplicity at small scales, right? So it was a huge discovery when we realized that everything around us is built out of particles, elementary particles, electrons, protons. The basic building blocks of matter are extremely simple. But I think it's equally important that when we go to large scales, the universe itself is like a giant elementary particle. It's extremely simple. And then, of course, some of the largest objects in the universe, the black holes, we're now able to detect. These are also extremely simple. I mean, they may be millions of times the mass of the sun, but they really are like just big elementary particles. So how physics attain simplicity at very tiny scales and at very large scales is, I think, the characteristic of today's physics. How do we unify physics and see its simplicity on small and large scales and its complexity in the middle? In a way, this tells you, so when I say the complexity is in the middle, suddenly you realize, well, perhaps we are the most complicated things in the universe, right? Because we're in the middle. And when we go to larger scales, we don't see anything more complicated than us. In fact, it goes the other way. The larger scales we go, we get things are simpler and simpler. So I think this means that in a certain sense, we may be the leading edge of complexity in the universe. And that is occurring on our scale, in the intermediate scale. On large and small scales, things are extremely simple.
That's amazing, and it's almost like time repeating itself, because it reminds me of Aristotle. So,
right,
we would be the
right.
Aristotle's Revenge. We would be the culmination of the universe. In other words, a conscious thinking organism is the most complex thing in the universe. There's a beauty to that, again, an elegance.
There is a beauty to that. Now, I was trained as an elementary particle physicist, right? And so for the last, 100 years, elementary particle physicists have been picturing the universe as built of building blocks, right? And you build it up into more and more and more complicated structures. And that mindset still underlies most thinking in so-called fundamental physics, in string theory. You ask a string theorist, how do you build a universe? Well, you have an awful lot of strings and you add them all together and you put in extra dimensions and multiple ingredients. And then a common, the outcome of string theory was what? It was the multiverse. If you go to larger and larger scales in the universe, it gets more and more complicated. That's where the string theory picture led to, and probably was inevitable in any picture that you build from building blocks from the bottom up. What I'm saying is that the observational evidence is that that is not how nature works. Nature works equally from the bottom up, and meaning small scales to large, and from large scales to small. And that second part, the large to small, is all about gravity. And so to understand that, we really need to understand gravity and the connections, particularly to quantum mechanics, because that's how you count states in a system, is using quantum mechanics. And that is a formalism we're only just developing now. So I'm being guided part by theoretical ideas, but in large part by observations. Observations are just telling us the universe works in this peculiar way, from small to large and from large to small, and we probably are the leading edge, the most complicated things in the universe. So it's a very different way of thinking about physics, and I think if it succeeds, it will lead to a revolution in physics just as important as the introduction of relativity or quantum mechanics, in which if you like, the starting point, the minimal ingredients are both at small scales and large scales.
Now, the genesis of the universe. We talked briefly earlier about the universe being pulled out of the ether, or whatever one wants to call it, whatever a universe is pulled out of. How does that happen?
Yeah, let's say it's, well, again, I'm working partly by analogy. There is a real phenomenon in nature where you can drag particles out of the vacuum, a strong electric field, and very, very beautiful process. Let's talk just a little bit about that process, because it really is stunningly beautiful, and it was understood in the early 1940s that this had to be possible. When you combine relativity and quantum mechanics, it was inevitable that particles could be dragged out of the vacuum. And let me talk a little bit about it. So if you're able to picture a particle going forwards in time, maybe think of time as the vertical direction, in space, we want to visualize it, and space as the horizontal directions. So a normal particle would go forward in time. you can also imagine a particle which travels backwards. And then what you can imagine is a particle which goes backwards in time, but instead of continuing backwards in time, it turns around and then goes forwards in time. And when it goes forwards in some other place in space, so it really performs a loop in space-time. It goes back in space-time and then forward. That was the picture realized in the 1940s, that when you combined relativity and quantum mechanics, that had to be possible. It had to be possible for a particle going backwards in time, which is actually an antiparticle, to turn into a particle going forwards in time, which is a normal particle. And so for an observer sort of looking at the universe at some time after this turnaround, they would say, oh, there are two particles. One is an antiparticle, one is a particle. Actually, they're just two facets of the same particle. It's just that it turns around in time. And that's our sort of unified picture of the universe. There are two sides to the universe. On one side, you could say it's going backwards in time, and on the other side, it's going forwards in time. But it's all a matter of perspective. Somebody else could say, oh no, I think of the particle as going backwards in time and the antiparticle going forwards in time. So you have to be very careful whose perspective you're talking about. So yes, rather than saying when you have this picture that a particle-antiparticle pair is created out of nothing, that picture really says, there's another interpretation of it, which says, no, there really isn't a particle-antiparticle pair. It's really just one particle, okay, that happens to have gone backwards in time and then turned around and went forwards in time. And you're just looking at it at one particular time, and you're seeing two particles because you see it going backwards through that moment of time and also going forwards through that moment of time. And this is actually a very old idea due to John Wheeler.
One electron.
And Wheeler used one electron. He said, maybe, we see billions of electrons and positrons or anti-electrons in the universe. There are more electrons than positrons, but in physics, we can create both of them. And so Wheeler said, well, what if they're all the same particle? And when we see it as a positron, it's just going backwards in time. And when we see it as electrons going forwards in time, well, then there's no mystery as to why they all have the same charge, because they're all the same particle. So instantly, you've explained why every electron has identical charge and every positron is exactly the opposite. Why? Because it's all the same particle. There is only one particle in the universe, right? So absolutely beautiful idea. And that idea may actually be realized in our cosmos, because we now have two sides of the universe. On one side, we have more particles going forwards in time, more electrons. On the other side, we have more going backwards in time. Those are the positrons, right? But maybe there is only one. Okay. In fact, maybe there's even zero. Net, and maybe it's all a closed, there's this single particle and it just goes around and around in this loop. And where it's going backwards on one side of the universe, say that's antimatter. Where it's going forwards, more of the time, that's matter. And the quantization of charge, the fact all particles have the same electric charge, is kind of automatically explained. So yeah, indeed, this is one of the directions we're pursuing, that maybe we can explain the quantization of charge. Another issue is the arrow of time. This is, again, one of those philosophical questions. Why does time seem to be going forward, away from the Big Bang? When the laws of physics are the same. When you reverse time, the laws are invariant. If you run a film of a physical process backwards, it's still a valid physical process. So where did this direct arrow of time come from? And so again, our picture of the cosmos gives us the opportunity to solve that problem. And this is something we're looking into very carefully, and we have a tentative solution to the problem of time. And indeed, the resolution is that there are parts of the universe where if you like, from our point of view, time is going backwards, and in our part, it's going forward, and somehow the whole does not violate the symmetry of the laws of physics. The standard picture of cosmology, where the universe starts small, ends up big, that violates the basic symmetry of the laws of physics under reversing time, because if you reverse time, you start big and you end small. Our picture doesn't do that because it has these two sides of the universe kind of going in opposite directions. And the whole is invariant under reversing time. So I think we have a chance to solve some of these kind of deep philosophical questions which have been unresolved for decades. And by the way, these are not simply academic, well, they are academic questions, but they're the basis for everything. So for example, when you use the laws of electricity and magnetism to figure out how particles influence each other, you can't use those laws unless you assume something about the direction of time. So for example, when I wiggle an electron, it will send out radio waves, and those radio waves will influence other charged particles to the future. But we always assume that wiggling an electron now does not influence particles to its past, because if we allowed that, we'd get into all kinds of conundra. What's going to happen to me?
Yeah, causality.
Causality. Am I influenced by something in my future? So we always, exactly. But the way we implement causality, and it's purely as a result of our observational fact that we see causality works, but the way we implement it in our equations is kind of ad hoc. We just put it in as an assumption. Oh, in order to preserve causality, we have to ignore some solutions to our equations and keep others. So we keep the causal solutions and we throw away the acausal ones. What I'm saying now is, in this kind of two-sided universe, we have an opportunity to mathematically solve that problem, to understand why it is that we have to throw away the acausal solutions. That may be imposed upon us by the mathematical consistency of the universe.
So let's get into this idea of a double-sided universe.
Yes.
First and foremost, a very popular thing within cosmology today, or if you want to call it cosmology, it might even be bigger than that, is the idea of a multiverse.
Yes.
Is this necessary, or is it knocked out in your model?
I would say the multiverse is a logical consequence of a certain mindset. The mindset, in brief, I think the multiverse is the most ridiculous scientific theory of all time, okay? Because a lot of things which are completely untested, and at its worst, it's just an excuse for saying, okay, well, we can't explain certain things about our universe, so we'll just assume there were lots of other universes, and we happen to be a random sample in the space of all universes. It has no explanatory power at all in the way that it's being used. I'm very much against the multiverse because it's not a tight framework. It's not a predictive framework. It's a kind of just so, which some people find satisfying, but I do not. So yeah, and then the other reason I don't like the multiverse is it seems to be inconsistent with observations. When the larger the scale we look at, the simpler the universe is. We don't see evidence of wild randomness on large scale. So, but the reason this kind of crazy hypothesis of the multiverse arose was because of the development of particle physics. People made colliders and they found electrons, protons, and then other particles like gluons and W bosons and neutrinos. And basically, as you went to bigger and bigger colliders, you saw more and more particles. So the whole pursuit of theoretical physics became about adding a new particle. Every time you did a new experiment, you saw a new particle. So you incorporated another particle into the model. The model got bigger and bigger, and this worked fantastically well. This philosophy of just adding stuff. It worked really well until 1980. And around 1980, the standard model was done. We'd seen all the particles which we have ever seen, but the theorists kept going. They kept adding things, okay? So the theorists kept adding more and more particles, and they made grand unified theories, which typically have hundreds of particles. And then they went to super unified theories, which have thousands of particles. And then they went to string theories, which have even more particles, and extra dimensions of space-time, which has many more additional parameters and possibilities. And basically, the theorists, I believe, went overboard. Experiment ran out of new particles, but theory kept going. And the logical consequence was the multiverse, because the theorists were constructing such complicated setups without any experimental foundation that they ended up in this kind of wild, crazy space of hypothetical universes. And by the way, not one of which have they successfully explained its beginning, because when people talk about the multiverse, these are people who don't tackle the real problem of what happened at the Big Bang. I just want to solve the universe we're in. I'd rather not speculate about other universes that we can't solve. I'd rather focus us on the problems which we know are real in our universe and try to solve. So yeah, I think the multiverse will go down as a sort of diversion from good physics. I'm very happy about it because it's diverted a lot of very smart people into speculations which I believe won't go anywhere, leaving the space of thinking about the real problems to only a few of us. And that's fine.
Again, it goes back to simplicity. A simpler universe is much easier to understand and probably, well, it's more probable. Now, let me ask you about this, though. There's one thing that the multiverse people tend to bring up that gets a little metaphysical, I suppose, the anthropic principle. Why should we be special in this universe?
Yes. So again, this is a very appealing at first sight, the anthropic argument. And I must admit, when I first came across it, I got very excited and I thought, let's recondition the, so for example, the expansion rate of the universe is called Hubble's constant, right? And what does that mean? It means the expansion rate as measured by Edwin Hubble, So when you calculate it, maybe you should, of course, assume a universe which is expanding, but maybe you do need to put in the astronomer. Maybe you need to put that in as part of your theoretical framework and ask exactly what did that particular astronomer see. That's fine. That's normal science. That's kind of taking into account the selection of observers and asking what they would actually see. That's just doing your science better and in more detail. So I think no one can object to the influence of the observer on the experiment. I mean, we know that in quantum mechanics. You must be very careful to understand the ways in which the observer, affects the final experimental observation. So that's all good. And the anthropic argument is if done in that way, would be completely acceptable. Unfortunately, it's not done in that way. It is applied in cases where we can't predict anything as a sort of excuse for why things might be that way. So typically, the most successful application of the anthropic principle was to explain the dark energy. And it explained it by saying, well, if the dark energy had been much bigger than we observe it, then it would have pulled us apart to expand so rapidly that we would never have formed galaxies. Then you get into the detail of that, and the assumptions behind it, which are many, 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 and it doesn't explain the number. It's more of an explanation which is sort of just a way of living with an awkward fact which you don't So I'm not in favor of that kind of argument because I think in order for science to progress, in a sense, we must keep looking for simplicity and looking for real explanations, meaning quantitative predictions based on what we already know, which can then be verified in experiment. And the trouble with the anthropic argument, it's never like that. It's always applied to situations where you know something, you've measured something, it feels a bit awkward, why is it like that? And then you develop this rationale for maybe it had to be that. And I find that very unsatisfactory. And I think particularly for the dark energy, because the dark energy is such a fundamental parameter in the universe. It's almost like, it's more fundamental than the mass of the proton. I mean, the energy of empty space is a number. Maybe everything should be referred to that number. Whereas what anthropic people say is, let's assume that number was random. There are parts of the universe in which that number is big, then parts where it's small, and then we sort of plucked our universe out of the hat, and it happened to take the value that it does. And I don't like that explanation because it's not got any real explanatory power or predictiveness. Whereas I think, if you think back to Maxwell or Einstein or Dirac, the theorists who built the Standard Model and our theory of gravity, would they have been satisfied with the anthropic explanations? And I'm very clear in my mind, the answer is no. They would say, come on, guys, be serious, build a real theory. So I think the appeal of the multiverse theory and the anthropic principle is very much a phase which modern physics is going through. I hope it does get through it, but I'm convinced it's not really not going to be a fruitful speculation. And I heard about the anthropic principle from Stephen Hawking, actually, who I was working with. And his endorsement of it made me take it really seriously. And I worked with him for a while, but to implement it carefully. But as soon as you try to do that, you realize it's really not an idea which is going anywhere. And so I formed that opinion about 15 years ago. And I must say, all subsequent developments have just confirmed it in my mind, that the anthropic principle is superficially attractive, but ultimately not a fruitful avenue for research.
Now, my last question for you is that, barring the multiverse as it's envisioned,
yes,
a dualistic view of the universe
would
imply an anti-universe. What would such a place be like?
Well, I think, again, go back to my picture of the particle antiparticle pair being created. It all depends on your point of view. So from the point of view of the antiparticle, it would say nothing any different from the particle. Okay. So if we live in part of the universe which is full of matter, we will describe things just in the same way as somebody living on the other side of the universe. It's just that our 2 points are opposite. So I think what I'm looking for is an explanation where essentially the universe we see around us is the most likely one. It's extremely simple. And the partner universe is really no different. It's only the partner because if we try to extrapolate our universe to a bigger picture, we find mathematically there's this partner, but it's really no different than where we are. So the framework I'm looking for, which I think is emerging, is the universe is much more unique than people have imagined, and that there is only one. You see, a very old problem with Big Bang cosmology is people say we can only see a certain distance, right? We can only see 13.7 million light years or some distance. Because if we try to look any further, we're looking right back at the Big Bang itself. And then people speculate what is there at large distances and so on. My preferred point of view is that the only thing that's really there is what we can see. And so the universe, in a sense, is a small place, right? It's not infinite in space. It's not really infinite in time. It's just that when we try to picture it, our classical picture encourages us to extrapolate, but that stuff doesn't really exist. It's like speculating about, green men on the other side of the moon. It doesn't really exist. So again, I believe we want to look for a unified picture of physics in which the universe basically is a small place. And it's as simple as it could possibly be, given the laws of physics. And what I see in the observations is, indications of that point of view, rather than a crazy multiverse or even an infinite random universe. I don't see any evidence for that. At the very least, we should explore both possibilities, and we'll see. I have a gut feeling about which is more likely to be fruitful. It will only really be fruitful if it makes predictions which others are unable to make. But the fact we can now explain the dark matter in a much simpler way than any multiverse theorist, is a real plus. And if the experiments come in behind our theory, I think ideas like the multiverse will gradually fade away because they haven't worked. They haven't predicted the neutrino mass. We've predicted it. If it turns out to be correct, our theory is obviously doing better. So that's how this will all be resolved. It'll be resolved by whoever makes the best predictions.
And ultimately, the old adage, the simplest explanation tends to be the correct one.
I do believe so. That's what motivates me, is that time and again in physics, these astonishingly simple theories turned out to be correct. Dirac's theory of the electron, he built it on certain assumptions, but it explained the positron, the anti-electron, without any further assumption. So Einstein's theory of gravity, he didn't build it to explain the universe. He built it to understand how to reconcile gravity with relativity. But it turned out to explain a million other phenomena as well in a very, very predictive way. So all these sort of foundational theories had properties there, very unique. They can't be dialed, They are what they are, and either they're right or they're wrong. And so at a certain conceptual level, they're extremely simple, extremely predictive. That's what we need to aim for in cosmology. And I believe ultimately that's the way it'll work. The universe will turn out to be indeed simple theoretically, simple observationally, and this will help us understand what is our place in the universe. I don't think we're a random, we're to some extent random, of course. Each of us is a random individual, but the fact that life emerged in the universe is very likely anything but a random occurrence.
Which it has a certain beauty and elegance in and of itself.
I hope so. It sounds mystical, but I don't think that should detract from it,
Well, one can say completely reasonably that we are the universe perceiving itself,
yes.
Which is amazing.
Yes, I love that idea. I'm driven by trying to find out the truth. I don't want our philosophical preconceptions to dominate. Proper science to be done and to be checked experimentally, mathematically. If it turns out that indeed we are, a way of the universe to conceptualize itself, that really helps us understand what we are. And indeed, that may be the case.
Doctor, we are out of time. This has been a fantastic discussion, a privilege really, and I thank you for being here, and I hope you'll come back sometime.
Thank you very much for having me. It's really been fun.
John, did you know that we've not checked the answering machine in 6 whole months? John? Oh dear. I guess I'll check the answering machine myself.
You have one new message. Where's the podcast go here? Want to listen to podcasts. I don't want to... Hold on, someone's at my door.
End of messages.
Oh dear. Well.
Message deleted. You have no new messages.